Hi, so today in this video we're going to be talking about chapter 5.2.2, which is transformation of the exponential function, stretches, compressions, and reflections. I've talked about a lot of this in my previous videos, mostly because I didn't realize what the homework would be asking for, but this time we're going to be talking about, like we said, compressions, stretches, and reflections. So there's a few things to know when you are doing this. We have this, right? This is our y-axis, this is our x-axis. If we're reflecting over our y-axis, let's say you have like a little heart here, or like this. If we're reflecting over our y-axis, we're basically flipping it over to this side, right? So it'll be like this instead. There are a few things to notice here. We are not changing our y values when we're flipping it. This y value and this y value are going to be the same for this graph. However, our x values are going to change. It will go from positive, whatever this is, to negative, whatever this is, and vice versa if you're flipping from the other direction. The next reflection is going to be over the x-axis, and this is when it does something like this, right? And one thing to note here is that the x values don't change at all, but the y values do. And the way to do, so let's say we have f of x is equal to, say, 2 to the x. If we want to flip it across the x-axis, so from here to here, what we can do is we can do like -3 or -1 times 2, like that kind of thing, -2 to the x. And it will go from like this to like that. And it will also stretch it by 3. The way to do it across the y-axis is to do -x up here. So it'll go like from this to this. When we're talking about stretches, if we have a stretch of, say, 2, so if our original graph is 2 to the x, 1, 2, 3, 4, 1, 2, 3, 4, our first point is always going to be 0, 1. Our second point is going to be 1 to our base, and then our -1 point is going to be 1 over our base. So our graph is going to look something like this, right? But if we're stretching it, and let me actually change this to be, say, 3. 1, 2, 3, 4, 5. This point is going to turn into 3 instead of 1. Let me change the color. So our first, instead of 0, 1, because basically all we're doing is we're timesing our y value by our stretch value. So this turns into 3. This will turn into 6, because 2 times 6. So 1, 2, 3, 4, 5, 6. And this will turn into, so 1/2 times 3 is 3/2. So it actually moves up a bit. Well, 1 sec. Yeah, so it does. It goes from from 1/2 to 3.5. I mean, not 3.5. 3/2, which is a little more than 1. So our new graph is going to look like this instead. It stretches upwards, see? If we had something like 1, let's say like 1/3 instead, what is going to happen is we're going to be timesing our y values by 1/3. So this will turn into something like this. This will turn into 2/3, which is a little less than, and this will turn into 1/2 times 1/3, even smaller, even itty bittier, and it will compress it basically, right? And that's our main transformations that we'll go over in this video. Getting into our problems, we have if the function f of x equals 3 of x is compressed by a factor of 2, what is the equation of the transformed function? So we're compressing by a factor of 2. Compress gives you the hint that we're going to be doing it by a fraction, 1/2 times 3 to the x. That is your new equation. You want to do f of x equals that. If 6x was transformed, which resulted in the function f of x equals 1/4 times 6x, the function was compressed by a factor of 4. If that doesn't work, try compress by a factor of 1/4, but I believe that it wants not the actual fraction. It's just troubleshooting. It'll be something along those lines. The function f of x equals 2x is transformed to be f of x equals 4 times 2x. What happens to the point 0, 1 on the function? Again, when we're stretching, it only will affect our y values. It won't affect our x values. So we'll multiply our y value by our stretch factor, which is 4. So our new value will be 0, 4. 1/2, our new value will be 1, 8. Then to graph it, we'll do 0, 4, 1, 8. Bloom. It'll look something like that. Once you have your 2 points, it will graph it for you. The function f of x equals 1/5 to the x is transformed to be f of x equals 1/3 times f of x, times 1/5 to the x. Express your answers as a point with coordinates written as integers or fractions in lowest terms. What happens to the point 0, 1 on the function after the transformation? So again, we're going to be multiplying our y value, so it will turn into 0, 1/3. What happens to the point 1, 1/5 on the function? F of x equals 1/5 to the x after the transformation. That will be 1/5 times 1/3, which is 1/15. So 1, 1/15. You'll probably get crazy things like that, yeah. What happens to the point 2, 16 when the function f of x is equal to 4x? 4 to the x is stretched by a factor of 3. So we'll do 3 times 4 to the x. It'll look something like that, but we don't even need that. We're just multiplying our y with our stretch factor. So 16 times 3, 8, 4, 48 it looks like. So 248. What happens to the point -2, 1/16 when the function f of x equals 4x is compressed to 1/4 of its height? So we'll just times this by 1/4, which is going to be -2, 1/64, because it is only affecting our y value. The function f of x equals 2 of x is reflected across the x-axis. What happens to the point 4, 16 that lies on the parent function after the transformation? Now, if you remember, reflecting across the x-axis sort of looks like this, because this is our x-axis. It's like looking at an ocean. This one's like looking at a waterfall for the y-axis. There's not really an easy way to remember that, I guess. But this is x-axis, side to side, y-axis, up and down. What happens to the point 4, 16? So our x value is going to stay the same, but our y value is going to turn into a negative. So 4, -16. The function f of x equals 2 of x is reflected across the y-axis. What happens to the point 4, 16 that lies on the parent function after the transformation? Important thing of this equation is the y-axis here. So here's our y-axis. We will flip it over. It will look like this. So our x value is going to change, but our y value is going to be the same. So we'll have -4, 16. Fill in the blanks. What transformations were performed on the parent function f of x equals 3 of x to get the function f of x equals -2, 3 to the x minus 4 plus 1? So this one will be the function has been reflected across the x-axis. And the reason why we know that is because of this -2. And has been stretched by a factor of 2. And not -2 because reflection covers that. The function has been horizontally shifted up by 1 and vertically shifted, that's the wrong, horizontal is side to side. Has been shifted right by 4 and vertically shifted up by 1. Easy peasy. The parent function, g of x, equals 1/3 to the x is compressed by 1/2 of its height, shifted vertically down 3 units, and shifted horizontally right by 1 unit. What's the equation? We are going to make sure that you're doing g of x if it says g of x. You want to make it stay the same. So if it's being compressed by 1/2 its height, we'll do 1/2 times 1/3 to the x minus 1, because we're going to the right, and then -3. Usually it's good to have parentheses like this or like this. I don't think it matters in this case just try around with your parentheses. If it's saying that's wrong, g of x equals 1/7. It's stretched by a factor of 6, so 6 times 1/7. Reflected across the y-axis, so that's going to be negative x, shifted vertically up 3 units, so plus 3. G of x equals this. This is our answer. All right, that's all the questions that I saw that were different. If you have any questions, please let me know, and I will answer them as soon as possible.